neighborhood of a point. When we talk about neighborhood of a point, we divide neighborhood of a point as follows. A set n is called neighborhood of point this. If there exists an open interval I, this open interval, such that this S0 belongs to the open interval, and the open interval is a subset of this n, then we say that n is a neighborhood of this this S0. So if they say that neighborhood, when a point is contained in an interval, then the interval that is a subset of a certain set, then that set is a neighborhood of the point. So neighborhood is being written in, is being denoted by this. So this sign means neighborhood. So remember that this can be written as this thing from the inequality. We can write it as minus epsilon is less than this, is less than epsilon, which can be written as this. This can be written as this, or we write it as this. That is, if you had minus epsilon, if you take minus epsilon to both sides, it becomes plus. Sorry, if you take minus S0 to both sides, it will become plus S0. So, which can be written in terms of interval like this. So in that case, we can rewrite this statement as a point S0 is this set is a neighborhood of S0 if there is an open interval I, such that I cannot write it as such that not belonging to this interval. So this I that we put here, this is the I. And this I, we have written it in terms of, so it will be better if you are writing it in terms of this. And in a case whereby S0 is not in that interval, so we say that we have a deleted neighborhood. This is deleted neighborhood. So it is written in this form, epsilon minus MBD, epsilon dash MBD, that is deleted neighborhood. At times, some people will use delta instead of epsilon, so we mean the same thing. Now let's consider the following theorem. This is the theorem: any open interval is a neighborhood of each of its points. So let's prove it. So to show that an open interval is a neighborhood of each of its points, so let us start by getting an open interval. Let this a comma b be an open interval. Let us take a point in this open interval. So we want to show that this open interval is a neighborhood of all these points. And what are we going to show? We only need to show that as this S not belonging to this this open interval, so this open interval must be a subset of another open of the open interval again. But we know that a set is a subset of itself. We all know that it says it's a subset of itself. That simply means that this set will be a subset of AB again, because by what we said there, a subset is a set is a subset of itself. So from that place, I can say that S now belonging to this open interval belonging to this is a subset of this open interval. So, and this is what we have shown by this is what we show from the definition of neighborhood. We said S naught, when it belongs to the interval must be a subset of this n, and the n here is our open interval. But the theorem now says that this open interval is a neighborhood, that is, it is this n already. And we have seen that this set is a subset of itself. So in that case, we have shown that any open interval is a neighborhood of each of its points. In a real sense, what that simply means is this: if you have an open interval A and B, so if you pick any point, let me pick a number. Let's say I have 2 and 12. Let me pick any point. Let's say 0.3. we know that within this open interval there contains infinite number of real numbers, because for instance if I say that 2, 12, there are many numbers inside it, because I can have 2.1, I can have 2.1.1, I can have 2.11, like that. There will be many numbers inside this place, many real numbers, so it will be many. So if I pick any element in this place now, we can create an open interval there. You can create an interval. Let's say this one is 2.5, let's say this one is 3.5. so you can see that this open interval contains this 0.3. I have created an open interval there within 3, which will contain this 3, and this open interval that I created here is still a subset of 2 and 12. So in that case, this 2 and 12, at whatever point we pick there, so this 2 and 12 is open. This 2 and 12, we say that is a neighborhood of whatever point we pick, because any point that we pick, we always get open interval inside it. But if you talk of closed interval, we can say that it's a neighborhood of all its points. So, but we can say that is a let's consider a closed interval. A closed interval is a neighborhood of all its points except A and B. This closed interval A and B is a neighborhood of all its points, because what this closed interval simply means is that A is less than or equal to X, is less than or equal to B. So what this thing simply means is A will be among the set. For instance, if you have 2 is less than S is less than 4, this thing will be 2, 3, 2 to 4. That is 2 will be there, and so on to 4. But if it is open interval now, if I say open interval 2, 4, it simply means that 2 and 4 are not part of the set. So it is very large. But this one now, 2 is there. When we say that open, in that case, let's assume that I want to create an open interval. Any number we pick from this place, we will always be creating open interval. Any number we pick between this line. But let me go and pick 2. If I go and pick these 2, I can only get a number in this place. I can't get a number from this because there's no more number again. Because this one, it ends in 2, because this thing says that it starts from 2 and ends in 4. If I pick 4, 2, I can be getting numbers here, but there is no number again. Unlike this one here, that 2 is not there. So whatever I pick, I don't even know where it ends. I don't even know where this one ends. So it is infinity. But this one now, it ends at 2 and it ends at 4. So if I pick 4, there will be no. I can't create an open interval. There will be nothing here. But although I can create from this place, but I can't create here. So that is the reason why we say that a closed interval, this is a neighborhood of all its points except A and B. Another one, this N, set of natural numbers. So it's not a neighborhood of any of its points. So for instance, if you consider natural number, let's say 1 to infinity, whatever anything we pick here, let me now say I pick open interval, let's say 4 and 7. So let's consider this open interval. This here now, there will exist infinite real numbers in this place, and there's no way there will be real numbers. There's no way a real number will be a subset of this N. So in that case, because for this thing to be, for N to be is how will I put it, neighborhood of its point. For N to be a neighborhood of its point, we must have that whatever element we pick. Let me say I pick 5. 5 must belong to N. N must be 5 must belong to an open interval that contains the 5, this open interval that contains the 5, and that open interval must be a subset of n. But the open interval we are considering here now contains a real infinite real numbers, and there's no way real number can be a subset of n. That is the reason why the natural set of natural number is not a neighborhood of any of its points. We have another theorem here. If A is a neighborhood of point S and A is a subset of B, then B will also be a neighborhood of S. So that is easy. We can prove it. So we can start by saying, since A is a neighborhood of S, then there exists an open interval this. If you remember our definition of neighborhood, there will exist an open interval such that S will belong to this, and this must be a subset of A. But A is a subset of B. So definitely S, this will be a subset of A, but A is a subset of B. So by transitive law, we can match them together by saying S belongs to this, and it to be a subset of B. And whenever we have it like this simply means that B is a neighborhood of X, and that completes the proof. So we have our theorem 3. The intersection of finite number of neighborhood of S is again neighborhood of S. So we want to prove it. We start by gathering many neighborhood of S. So we start by saying, let AI be collection of neighborhoods of X. AI there simply means A1, A2 up to AN. Let's assume that all of them are neighborhood of S0. So what we want to show is that we want to show that their intersection. This is what we want to show. We want to show that AI is equal to this, their intersection. This is their intersection, that is A1 intersection A2 up to intersection AN. This is how we write it. We just put intersection, then we put AI. This thing simply means A1 intersection A2 like that. And everything we represented it by A. So we want to show that A is a neighborhood of X. Now, since AI are neighborhoods of X, that is, since A1 is a neighborhood, A2 is a neighborhood, all of them like that, since they are all neighborhood, so then there exist open intervals. There is open intervals such that those open intervals will contain S. So we have the following. S belongs to this one. Remember this definition of neighborhood. Since we have assumed here, we have agreed that AI is a neighborhood. So A1, we have this. You know, it is S minus epsilon. But since we have more sets, so I've represented them by epsilon 1, epsilon 2, like that, up till we get to xn. So from this place, we need only one epsilon. So if you consider this, if you let this epsilon be minimum of all this one, minimum of epsilon 1, epsilon 2, and epsilon 3. So we are going to have that X belongs to this S minus epsilon, comma S plus epsilon. So this will be a subset of because it's a minimum of this, so it will be a subset of S minus, let me use SI for all of them, SI, comma S plus epsilon I. So and all this will be subset of all of them. I put I there as A1, A2, A3. So this will also be subset of this. It will implies S is a I've rewritten it. I put intersection to this A. As you can see, I wrote the same thing. So if all these are subset of A, so they will still be subset of their intersections. So which I can shorten and write it as this. By transitive law, I can leave this and take this. It's a subset of this. And we have said that let all these things be A. This is this S plus I is a subset of A. So this implies that A is a neighborhood of X. And don't forget that A is the intersection of finite number of neighborhood of X. Oh, and that completes the proof. We have shown that the finite intersection of open set, finite intersection of neighborhood of X is also a neighborhood of X. And that completes the proof. Another interesting one, limit point of a set. So we want to consider limit point of set A. So let R be a real number. A point S in this A is said to be a limit point, or we call it accumulation point or cluster point. So this point X inside this A is called a limit point of A. If every neighborhood of X contains another point of A, that is, if you have neighborhood that is containing S, if it contains another point of A, then we say that is a neighbor, point here is a limit point. So from this place we can write it in a symbolical way. Symbolically, if this a point X, this point X here is called a limit point of A, if for every neighborhood of X, that is, if there exists any neighborhood that is containing this X, intersection this A minus X, if it is non-empty, if it's not equal to empty set, then we say that this is a condition to show that a point is a neighborhood of a set. So another definition, if S is not a limit point of A, then there exists a neighborhood of S such that n intersection A is empty. So this is how to know that this point is not a neighborhood. If n intersection that A is empty, then we say that X is not a limit point of A. So another important definition. Now, derived set. So the set of all limit points of A, so it's called the derived set of A. So we write it in this, we write it like this, denoted as this. So the set of all the limit points, so it's called a derived set. So let's consider this. We have a set A to be 1, 2, 3 here, and let's consider this interval, the interval 1, 4, open interval 1, 4. So let's find the derived set of this this A. Now let's pick all the points here. Let's consider 1. You observe that 1 belongs to A. But if you look at this set, this is an open interval. So 1 does not belong to the, although we have open interval 1, 4. So open interval here means that 1 does not belong to it. So in that case, by definition, 1 here is considered 1 does not belong to this interval. So you can see that 1 is not a limit point. In fact, by definition of the limit point, we say that it's a limit point of A if every neighborhood of X, that is every interval, every open interval that contains S. So you see that this open interval does not contain 1. So in that case, 1 is not there. But let's consider 2. 2 belongs to A. You see that 2 belongs to the open A because this is in between 1 and 4. So in that case, 2 belongs to the interval 2. And by definition, they said if that neighborhood contains the 2 that we are talking about, the neighborhood as well must contain another point of A. So the question is that 2 is there, Does I contains another point of A? So this is another point of A, which is 3. So you see that 3 also belongs to I. So in this case, 2 and 3, they are limit points of A. So in that case, if I want to find the derived set will be 2, 3. So that is the derived set of this set. So that is the definition, and we can go by this too. The n intersection A minus S, it must not be empty. If it is empty, then we will say that that point is not a limit point. Let's consider another example. So every point of real number is a limit point. Every point of the real number is a limit point, and that simply means that the derived set of the limit point is also a limit. The derived set of the real number is also the real number. Also, for every s in a real number, so for every s in a real number is a limit point of Q. So what is our Q? Q means rational number. So that simply means that every real number is a limit point of rational number. So in that case, the derived set of rational number is the real number. So integer has no limit point, n has no limit point. So we have talked about that under neighborhood. Natural number and integer, they have no limit, but because they are not neighborhood of their point. Because if I consider natural number, inside natural number, there are infinitely many real numbers, and real numbers can never be subset of natural number, and they can also be subset of an integer. So in that case, integer and real number, both of them have no limit point. So in that case, their limit point is empty. So their derived set is an empty set. Okay, in our next video, we'll now talk about another thing is this first species. We say that a set is first species if it has only finite number of derived sets, and if a set has infinite number of derived sets, then we say that it's of second species. So in our next video, we'll now talk about open and closed set, because open and closed set, they depend on all these things we are talking about. Have a nice day.